Now I'm going to introduce two important symbols or tensors in tensor calculus. The first one is the Kronecker Delta, and the second one is the permutation symbol. These two tensors are frequently used in different vector identities or in different equations in continuum mechanics, for example, or in general relativity theorem. The Kronecker Delta, pay attention to the spelling. The Kronecker Delta is the discrete version of the Dirac's delta function. Perhaps you know the definition of the Dirac's delta function, which is a continuous function with a singularity at the origin and is related to the Heaviside function. Here we have a discrete version of the Dirac's delta, which is called the Kronecker Delta. The Kronecker Delta is a second-order symmetric isotropic tensor. I have to record some other videos about the definition of for example, symmetric tensor or isotropic tensor. But simply speaking, symmetric tensor is a kind of tensor which the magnitude or the value of a tensor does not change when the indices are interchanged. Based on the definition of the delta function, you can see that it is a symmetric tensor. The definition is here, that the Kronecker delta, you see here two indices, so this is a second-order tensor. When two indices are not identical, the result is a zero. And when otherwise, or when the indices are identical, the result is unity. This is a simple definition of the important Kronecker delta function, or tensor. The translation of this tensor in Gibbs vector notation is the identity matrix. The identity matrix is a matrix which the diagonal components are 1 and others are 0. So you see, when you interchange the indices, the result of the delta function is the same. It means that delta, for example, 1, 2 is 0, and again delta 2, 1 is 0. Delta 1, 1 is 1, and delta, again, 1, 1 is 1. So the Kronecker delta is a symmetric tensor. Another important characteristic of the Kronecker delta is when a tensor of any order. You see, this circle is an arbitrary tensor. The indices are I, j, k, etc. When the delta, Kronecker delta, is multiplied by an arbitrary tensor, the indices of that delta function are L and J. You have to find the second index of the delta in this tensor. You see, j is the second index. And then replace that index with the first index of the delta function. Okay, so the j here should be changed to L, because the second index is j and the first index is L. So the result is ILK, IJK, ILK. So, as you see that the Kronecker delta select entries. For example, you don't like j and you want to omit it and replace it with another index, for example L. So you multiply a Kronecker delta with this one is the hateful index, and L is the index you like. So this product eliminates j and replaces the L. So another name of the Kronecker delta is the substitution tensor, because its duty is to substitute one index instead of another. You can easily perform this substitution procedure like what I did to any other tensor. There is a very well-known identity based on the Einstein's summation rule. Delta II, when the indices of the delta, Kronecker delta, are identical, it means that these indices are not non-repeating anymore. They are dummy variables, and you have to perform the Einstein summation rule. So delta I is equal to delta 1, 1 plus delta 2, 2 plus delta 3, 3 based on summation convention. As we have defined here, because the indices of three terms are identical, all of them are equal to 1, so the result is 3. This is a very important identity and the simplest identity in tensor calculus.